Good morning. Thank you for the last video share views 150 plus. This time I am taking the topic of flip-flop. I am Priya Sharma, Assistant Professor of Department of Electronics and Communication Engineering from SIRT Bhopal Sage Group, Sage Anand. Let's begin with the topic of flip-flop. A flip-flop is a sequential circuit with two stable states that can be used to store the binary data. The stored data can be changed by applying the inputs. Flip-flops are the fundamental building blocks of digital electronic systems, which are used in computers, communications, and many other types of systems. These are used as a data storage elements and are the basic storage element in sequential logic. Basically, there are four types of flip-flops. SR, which stands for set and reset flip-flop, JK flip-flop, D or the data flip-flop, and last but not the least, T or the toggle flip-flop. These are the circuit diagrams having the pin diagrams, which are having S and R as the inputs and Q complement as the outputs, having the preset and the clear pins. Then we have the JK flip-flop with J and K as the input and Q complement as the outputs, having the preset and the clear inputs. The preset and clear are used so that the previous output can be cleared or can be set again for the present input. Again, for the data flip-flop, we have a single input that is D pin and two outputs, which is one is the normal and the inverted output, and with the preset and clear pins. Last, the toggle flip-flop also has a one input and two output flip-flop. Let's start with the SR flip-flop. This is the most common flip-flop on the all. This simple flip-flop circuit has a set input S and a reset input R and a clock. In this system, when you set S as active, the output Q will be high and would be Q bar would be low. Once the outputs are established, the wiring of the circuit is maintained until the S or the R goes high or the power is turned off. The clock is connected, resulting in low outputs when the clock input is low. In this situation, the changes in the S or the R of the input of the flip-flop will not affect its output. As shown above, it is the simplest and the easiest to understand. The two outputs are shown are the inverse of each other, as I told you earlier. So coming to the truth table of the SR flip-flop, it is when the clock pulse is not given and S and R in the don't care condition, whether it is 0 or 1, it doesn't matter. The output will remain as in they are stored in the memory or in the previous state, and the future output will be the present output. When the clock is set 1 for rest of the inputs and the maximum possible combinations of S and R are taken, the Q and Q dash will result in these. But when S and R are given 1, 1, this condition is not used in this flip-flop. This is the major drawback of SR flip-flop, which has been overcome in the JK flip-flop. We'll continue to in a while. Coming to the characteristic table, which is derived from the truth table of the SR flip-flop, having the inputs present output S and R, and the output is taken as the future output Qn plus 1. These are the possible combinations and the output comes out to be like this. Then from the characteristic table, we derive the excitation table, having the inputs as present output, future output, and the outputs as the S and R. This is the main table for each flip-flop. Excitation table of each and every flip-flop is very important. From there we derive the characteristic equation. So the characteristic equation of the SR flip-flop is given as Qn plus 1 equal to S plus R dash Qn. Now coming to the JK flip-flop, the JK flip-flop is the improvement of SR flip-flop. As I told you earlier, that due to the undefined state in the SR flip-flop, another flip-flop is required in the electronics. The JK flip-flop is an improvement of the SR flip-flop, in which where S and R equal to 1 is not a problem. It is similar to SR flip-flop. The only difference is that we used a feedback in this. That is, the output is fed back to the inputs. That is, the normal output, that is Q, is fed back to K, and the complemented output is fed back to the J. Doing this overcomes the situation when S and R is not a problem. This is the truth table of the JK flip-flop, in which the input condition J equal to K equal to 1, this one. gives an output inverting the output state. However, the outputs are the same when one tests the circuit practically. In simple words, if J and K data input are different, that is high or low, that means these conditions 0, 1 and 1, 0, then the output Q takes the value of J. That is, if 0, 1 is taken, output will be 0, 1, 0 is taken, output will be 1. So the Q takes the value of J and the next clock edge. If J and K both are low in this condition, then no changes occur. That is, it remains in the present state only. If J and K are both high at the clock edge, then the output will toggle from one state to the other. JK flip-flop can function as a set or a reset flip-flop. So next is the characteristic table of the JK flip-flop, which has been derived from the truth table of the JK flip-flop. Then the inputs will be the present output Qn, J and K, and all the possible combinations of the basic circuit 2 to the power n, that is 2 to the power 3, 8 combinations. And we get these as the outputs. Coming to the excitation table, which is again very important. When 0, 0 is on the future output and the present output, we get 0 cross. 0, 1, 1 cross. For 1, 0, we get cross 1. And for 1, 1, we get cross 0. From this, when we solve using K map, this equation will be derived Qn plus 1 equal to JQn dash plus K dash Qn, which is known as the characteristic equation of the JK flip-flop. Coming to the D flip-flop or a data flip-flop is a better alternative that is very popular with digital electronics. They are commonly used for counters and shift registers and for input synchronization. In the D flip-flop, the output can only be changed at the clock edge. And if the input changes at the other times, the output will be unaffected. In this, the SR flip-flop is taken and we have combined the inputs of S and R through a NOT gate and given to the latch. Only difference is this. So this is the truth table. And how do you derive the characteristic table of the flip-flop? For the 0 condition, when clock is not given and the input is in don't care condition, the output is Qn. When clock is set high for rest of the inputs and the possible combinations are taken for the inputs, that is 0 and 1, the output is the same as it follows the input. From the characteristic table, we derive the possible combinations 0, 0, 0, 1, 1, 0, 1, 1. For 0, 0, that is for Qn equal to 0 and D equal to 0. The output Qn plus 1 is 0. For Qn 0, D as 1. D as 1, we get 1. The Qn plus 1 will follow the D. 0, 1, 0, 1, 0, 1, 0, 1. Same is the excitation table. It will follow the output. 0, 1, 0, 1, 0. From there, solving through K map, we get the characteristic equation as Qn plus 1 is equal to D for the D flip-flop. Coming for the T flip-flop, a T flip-flop is like a JK flip-flop. These are basically single input versions of the JK flip-flops. This modified form of the JK is obtained by connecting inputs of J and K together. It has only one input along with the clock input. These flip-flops are called T flip-flop because of their ability to complement their state, that is toggle, hence they are named as toggle flip-flop, as I told you earlier in the start of this presentation. So we have combined these two inputs of the JK flip-flop and made it a single input. This is the truth table. Earlier, when the clock is 0 and the input is at don't care condition, the output is Qn. When the clock is set high for rest of the inputs and possible combinations of T are taken, we get Qn, Qn dash, that is complement of each other. From this truth table, we derive the characteristic table, that is at 0, we get 0, at 1, we get 1. When the clock is 0, we get the complement of this 0. For 0, we get 1, for 1, we get 0. And from the characteristic table, we derive the excitation table, which is as follows. From the solving through K map, we get the characteristic equation for T flip-flop also, that is Qn plus 1 equal to TQn dash plus Qn T dash. So these are the basic flip-flops of our digital electronics. Having the applications, these are widely used in making counters, in frequency dividers, in shift registers, and in storage registers. I hope so that you are very clear with now the flip-flops and its working, its excitation truth table and characteristic table plus its characteristic equation. Hope to see you soon. Thank you. Sejananda.